Okay, so we just went through the transformations of graphs section of the algebra textbook. Before we work example problems, I wanted to make a video showing all of those concepts applied for an equation with a coordinate system other than the Cartesian coordinate system. Everything's the exact same concept. It's all the exact same concepts. So what we're going to do is take a look at a function and a relation that's not a function in polar coordinates, apply the different kinds of transformations just like we did in the Cartesian coordinate system in the previous video, and see how it's all the same thing. Okay, so here is a function in polar coordinates, and here is a relation. It's not a function. The graphing software that I'm using, Desmos, it only graphs polar coordinates that are linear in R. So just consisting of R to the first power. And so I couldn't graph this, but once we take a look at how this graph changes with the transformations, and if you've watched the previous video and saw how we worked with relations, a relation like this in a Cartesian coordinate system, I think it'll be pretty clear to you how transformations work in any coordinate system. So graphically, we'll just look at this function here. And then also just a reminder, I talked about this in the previous video, but you could have more than two variables and everything, the concepts are the exact same. So if you had like a cylindrical coordinate system, so you had potentially a z variable, you could imagine transforming the graph, like translating the graph along any of the coordinate directions, doing a vertical stretch or shrink along any of the coordinate directions, doing a rotation about any of the coordinate directions. And it's all the exact same concepts. It's the exact same thing that we're doing here in 2D. You just do those exact same things in 3D. Or even if it's more than three variables, when you get to more than three variables, you just have to abstractly think about the idea of, okay, I'm translating the graph along the W axis, which is like maybe like the fifth variable or something. And even more than that, we talked about how if you have a function that has like more than one input and even more than one output, that can still be a function. We talked about how that is, like a vector valued function, for example. It's the same thing. You can, for all the examples we're doing, we can apply translations and shifts and stretches on any input or output axis. So it's the same thing. If you've got more than one output, like a vector valued function, so like if you think about a vector field, think about it in 3D. So you have X, Y, Z. You could specify a position in X, Y, Z, that's the input. And then at some point in space, the output is a vector, which has 3 dimensions, or 4 dimensions. You'd have the magnitude of the vector and then the 3 coordinate direction angles. Or no, I guess it'd be, I think it'd be 3 dimensions. Well, you get the idea. You would have like 3 inputs and then there would be more than one output at each point in space. But like the output would be, you make another graph over here, and this would be the magnitude, the x component of the vector, the y component of the vector, the z component of the vector. And so you could imagine shifting the equation along any of those directions. Okay, so you've got here's x, y, z, and this is you specify a point in space, and that point maps to a vector in 3D space. That's whose tail is at that point. And so you need more than just one variable for that. So you've got more than one input mapping to more than one output, but you can shift. You can imagine, quote unquote, abstractly shifting the graph along these directions or along the output directions, because you'd have some sort of an equation that's got 6 variables in it. Okay, so let's just focus on this equation here. We'll come back to this equation later. Here is the graph of this equation, and this is zoomed out a good bit just so you can see the full equation. You know, this goes from R all the way out to the radius equal to 1,000. But what we're going to do is, when we do the transformations, we're going to zoom in here so we can actually see, we can look and see like the 1 or 2 radii shift. And we could see the amount of theta shifted. Okay, so here's the basic function. Let's do a translation, a shift in the positive R direction 3 units. So how do we do that? If we want to shift it in the positive R direction, we just go to every single R variable. Here it's simple because there's just one R variable. We go to every single r variable and we subtract 3 from it. So we subtract 3, not add. We're going in the positive r direction, so we subtract. So we would do r minus 3 is equal to theta squared That's it. So what happens if, let's plot this. Okay, the green is the shifted function. And what you can see is, like, look at this point here on the basic function, this point here. At this value of theta, the same value of theta, if we go out 1, 2, 3 units, there it is. The theta value of every single point didn't change. It's just the r value of every single point increased by 3. So every point went from r theta to r plus 3. R plus 3 theta. That's what happened. Okay, now we're not going to plot this, but for this relation here, if we wanted to shift this in the r direction, we saw this in the previous video in the Cartesian coordinate system, it would be the exact same concept. We'd see a graph here for this relation, and if we want to shift it in the r direction, we would do this. Sine of r, or no, it'd be minus 3 theta That's it. And that would be shifted in the r direction, positive r direction, 3 units. Okay, let's shift. Here's the basic function. Here's the plot of this. Let's shift this in the theta direction. The positive theta direction will do, so this is pi over 6. We'll do pi over 12. So we'll shift it this amount in the theta direction, the positive theta direction. Okay, so what we do is we subtract pi over 12 from every single theta variable in the entire equation. So we get r is equal to there we go. So let's take a look at this graph. Okay, the green is this shifted graph. And what you do is you look at, for a constant value of r, let's look at this point. Here's at this value of r, look, this got shifted by this amount. See? It's like a rigid body rotation. This didn't, the graph didn't change shape, it just rotated. What happened is the r, we went from r theta, the r at each point didn't change, but each theta was added pi over 12. That's what happened. Okay, if we come to this, the relation here would be the same idea. Just theta minus pi over 12 on each of the thetas. All right, let's now shrink the graph about the r-axis by a factor of 2. How do we do this? If we want to shrink it by a factor of 2, that means that we want to go from, we're starting at r theta here, and then we want to make it 1/2 r theta each point. How do we do that? We multiply every single r by 2. Well, there's only one r here, so that's it. If we want to do the same thing here, we would do 2r like that. Like that. That would shrink this graph about the r-axis by a factor of 2. So divide every r coordinate by 2 without changing the theta coordinate. All right, let's see what this graph looks like. Okay, so again, let's take a look here. We're at this radius, and we don't change the theta, and so we're at about 6 here, and we come down to 3. So every single at every single theta value, if you follow that constant theta line, every single r value has been divided by 2. Down here, this is at this theta, so you would see this is the theta line. This is about halfway. You divide this by 2, you're here. Okay, let's now stretch the graph by a factor of 2 about the theta axis. So we want to go from r theta to r2 theta. To do this, we multiply every single theta value by 1/2. Okay, what does this graph look like? All right, this is a little different looking, but it's still the same concept. If we look at this point here, we start at this r value, and then we multiply the theta by 2. So this is 1, 2, 3, 4. Now we go 1, 2, 3, 4. You see? Same idea. If we wanted to stretch by a factor of 2 about the theta axis, just put 1/2 theta on all the thetas here. All right, now a mirror flip. Let's do a mirror flip about the r axis. To do a mirror flip about the r axis, we put a -1, or just a minus sign, in front of all of the theta variables. So it's the opposite. So to mirror flip about the r axis, we do this. So we just put 5 over minus theta, so that's just minus 5 over theta, minus, and then let's see what this graph looks like. So remember, the idea is we're taking every r theta point, and here we're turning it into r minus theta, which if you remember from the Cartesian coordinate system, that's flipping about the r axis. If you take every xy point and do x minus y, you're flipping about the x-axis. You're going from above the x-axis to below, or vice versa. Okay, so it's hard to see this as a flip. We'll see a better visual of the flip when we do about the theta axis. But in fact, let's come back to this one. Let's do a flip about the theta axis. So to flip about the theta axis, we do minus r and that's it. Theta squared plus 5 over theta minus. Okay, so this, all right, so what we've done is every single point is minus r theta. So you take this point and then this becomes minus r. So you go from here in just the other direction, and you see you're flipping about the theta axis. You see? This is r. Now it comes to minus r. You flipped about the theta axis. We went from this theta direction to this theta direction. Okay, now let's come back to flipping about the r axis. When everything was minus theta. Again, we went every point did like this. So you can imagine here is this, kind of close to pi over 3. Well, instead, we did that. We went in the negative direction. So we went to like here. Right? This is pi over 3. This is negative pi over 3. This is harder to see, but that's the idea. Okay, so that's transformations of graphs in coordinates other than the Cartesian coordinate system. Now let's work some example problems from section 2.6. Some transformations of graphs example problems.